Okay, so we're going to start another topic, which is state space search. This lecture was originally written for, or it's written in terms of Charm++. You already know Charm++. You got 2 lectures in it, so it's not a bad thing there. But the overall conceptual framework that I'm describing is independent of Charm++, and that encyclopedia article will describe the framework, which is all that you need to know. So the class of problem we are looking at is called state space search or combinatorial search, or you can even think of it as tree structured computations, but that's distinct from tree structured data. There are algorithms that are tree structured data, but this is where, well, let's just describe what it is and then go from there. So what we're going to do is go through these classes of problems, divide and conquer, search for a solution, say n queens problem, and I'll mention why you need quiescence detection for some of these problems. Then A star. How many of you heard of A star? Okay, those of you who have done AI know A star algorithm. So practical implementations of A star, and if you go about doing A star in parallel, a modification turns out to be useful called IDA star. Bidirectional search, and we may touch upon some of these other problems, but these I think I will go a little bit more in detail of. So given a parallel machine, how to do these combinatorial type problems faster? The simplest one is, well, it's just a plug for Charm++. It turns out Charm++ was originally designed for these kinds of problems, so it is very useful for that. So not char arrays, but singleton chars. But I think what I would do is I would demote the Charm++ issues here. Only occasionally we'll use them to illustrate the point. Let's just focus on the conceptual part. One kind of problem that you encounter is divide and conquer. In this kind of problem, and again, forget chars. You have a problem. To solve this problem, you divide into k subproblems, and each one of those k subproblems need to be solved again recursively. And then you might need to combine the solutions from the children to form the solution for the parent. Quicksort is an example of that. So is, let's say, adaptive quadrature for integration or something like that. So there's a bunch of algorithms that are numerical, that are divide and conquer in nature. Fibonacci, which is a silly algorithm. Fibonacci can be done in logarithmic time, not even the linear time that you all know about. And so, but you know, that's an example of a divide and conquer algorithm. So, and search for any solution is similar, so we'll treat them together. So this is the state space search type problem. What does that mean? Let's look at n queens problem, right? How many of you know roughly the chessboard? How many of you don't know the chessboard and how pieces move? Everyone knows, or everyone is asleep. Okay, either way, I'm okay. So let's say you have an n by n chessboard, and you want to place n queens on it. A queen is a piece that attacks along straight lines, along the rows, columns, or diagonals, right? And so you want to place them such that they don't attack each other, n of them. That means every row must have one, every column must have one, because otherwise n won't fit into n. Pigeonhole principle tells you that they all must go to different rows. And so n rows, each row is occupied, each column is occupied, and then they must not attack along diagonals either. So how can you find a configuration that satisfies this characteristic, this definition? And a way of formulating an algorithm for this is to begin with a state which is an empty board, right? Begin with an empty board. And then given a board, place the queen in the first empty row, first row that has nothing in it, and there'll be n possible places to place it, right? And so that's an n-way branching tree, right? And so a state space search problem is one in which you're given a definition of states, and you're given a definition of start state, and you're given operators that generate new states given old state. So here the operator is first empty row, place a queen in it somewhere. That's the operator in one of the n places. And so you get n minus n operators that place queen in n different places. And so you get n successor states. Some of them will be immediately invalid, like placing it in the same column as the previous queen, right? And so some of them will be invalid because they attack some other queens through diagonals and so on. And so, yeah, invalid ones you can throw away, and then for every valid one, for every node, when you come to it, you say, I'm looking at this node. Is it invalid? Forget it. If it is valid, then let me generate its children and fire work to do them, right? Basically, you're firing work for doing each one of the child. Now, if each one of the children. And now, if that's the case, sequentially, you'll just express it recursively. In parallel, what do you have to do? In parallel, it also seems very natural. Just fire a piece of, fire some work, a char if you're doing it in Charm++, for a task in general for doing, exploring that subtree, right? So, and then of course, this one is a search for a feasible solution. Either you can look for one solution for 8 queens. How many solutions are there? Anyone knows? 92. There are 92 solutions for 8 queens. And it's interesting why it's 92 and not 96. Rotational symmetry means any solution that you find, if you rotate it, you will get another solution, right? And so, but anyways, if you are interested in that, look at that. But if as soon as you find, one problem is find all 92 solutions. Another problem is find a solution, right? And so those two problems are different in terms of their parallel performance characteristics. So the thing is, if you're looking for just any one feasible solution, as soon as you find one, you want to stop. Then how do you stop the search after the solution is found? After a solution is found. If you're doing it in MPI, this stuff talks about charm. In charm, you have a node, you pick it up, a char gets created for it, you look at it, if it's invalid, then exit. If it is valid, then create the children. In fact, why wait until it finds it's invalid? When I create the children, if they are invalid, I don't fire task for them. So I just fire a task for every valid child, and they go live somewhere. Well, if you're not doing charm, then you have to randomly pick a processor or somehow pick a processor on which to do it. In an MPI, you will just say, let's say one strategy is to randomly select a processor. And then you have to keep doing those receives and putting them in a queue and do something with it. Or you can just locally enqueue it and from time to time move work around. If you're idle, request some work from someone else. That's called work stealing. But if you're doing it in this charm style thing, as soon as you find, whichever style you're doing it, as soon as you find a solution, processor 392 found a solution. And one solution is all that we're looking for. So we have to stop. How do you stop everyone? So sounds like we should send a message to all processors and yeah, you cannot call CK exit because you might be doing some other stuff after finding it. So it's not enough to tell all the process, hey, shut down. It's not shut down. This phase is over. We might have to do something else afterwards. How do you do that? Well, you can tell your parent, say, hey, I found a solution. You tell your parent object, which tells its parent object, which tells its parent object until you come to the root. And then root can tell its children saying, hey, other children, say, hey, don't search anymore. We found a solution. And that wave can go on and then terminate the whole activity. Will this work? Yes?
There's no way to broadcast to a set of charms unless they're in an array, right? So like if they're not in an array, we can't do a broadcast.
Yeah, but you can broadcast to processors or something like that. The thing is, when would you pay attention to that broadcast, right? The problem is, if you are one of these objects that is being created, you get created. Your work is, as soon as you get started, you look at your valid, okay, create children, fire work for it. And then you will look for some other message or something, right? So that object has no chance to terminate itself before it finds out that it doesn't need to do anything. So you could do it by storing a flag on every processor that you check, and you somehow have to set that flag ahead of time. And every time you get a message, you can say, hey, are we terminated? If so, don't do any one of that, right? Or else, you can send a message to a parent. If you only want to express it in terms of parent and children, you send a message to your parent saying, hey, I just got created, I want to create more children, but tell me, do I have your permission, basically, right? And so the parent then would have gotten a kill message and will say, no, we just got a termination message, don't expand further, right? So that's an idea there. But this is, I think I'll skip over questions, that's charm specific. One interesting problem is, if you're just interested in finding one solution, how do you go about speeding that up? Normally, sequentially, you would have ordered your search. When you create children, you would say, oh, that one is more likely, that child is more likely to have a solution, I'll explore that first. So there is certain kind of ordering that you would follow sequentially. How would you do that, use that heuristic in parallel? Well, you are exploring things in parallel. There is just, you have to go to the second child and the third child, because otherwise you have no way of exploiting the processors you have available. So another problem is randomly searching along in parallel, where everyone generates a task whenever they get created. You may end up simulating a breadth-first search. A tree of depth 100 can have, if it is binary, can have 2 to the power 100 nodes. And if they can be all created at once, they will occupy a huge amount of memory. Well, actually, 2 to the power 100 is horrible, so you won't have time to finish it. But let's say 40, right? 2 to the power 40, you can actually do that much work, but you don't have that much memory. And so you need to explore the tree in a depth-first search manner. But if you do depth-first, then you have another problem, which is that you don't have enough parallelism. So a particular idea turns out to be very useful, which is priorities. So if you are X, every node in the tree has a priority. The root has a priority that's empty. Priority is a bit vector of some fixed length. The root's bit vector is of length 0. And if your priority is X, then, and if you have 3 children, then you need 2 bits to distinguish between children. So let's say your children are 0, 0, 0, 1, 1, 0. And so their priorities are X, 0, 0, X, 0, 1, X, 1, 0. What this does is every descendant of this guy will be smaller than, and therefore has higher priority than, any descendant of X1, 0. Because it has a suffix property. All of these guys will begin with X0, 1. And anything that begins with X0, 1, you define priorities in a lexicographic ordering. And so anyone which begins with X1, 0 will be larger than that. Higher priority is smaller number, like A is smaller than B. That's a lexicographic or dictionary ordering. And so by dictionary ordering, these guys will get higher priority. So if you now keep track of priorities when you process work, then you will get a good behavior in terms of going to the left tree first. In fact, if you implement this in a shared memory machine, what you would get would be something like this. The tree that is currently being explored would look like a triangle. To the left of it is the part that has not been explored, and to the right has been already explored, and to the right is the part that has not yet been explored. So you can see that everything here has kind of the bit vector priorities will naturally end up doing this. You can convince yourself that this thing has a shape of a broom sweep, so we just called it a broom sweep search, because look at that, that's the stick, that's the broom, and you're sweeping through the whole search space. And in fact, the memory utilization is pretty low. Depth of the tree only, and here this part is where processors are, so the number of leaves here is equal to the number of processors, and so the internal nodes are also proportional to the number of processors. So it's essentially P plus D is the memory requirement that you get from this. Now, let's do at least one other type of search that's more fun, the A star algorithm and IDA star algorithm. The A star search is the idea that you're looking for some kind of optimality. In the simplest case, you're looking for this, the smallest path length. So for example, if you're given a 15 puzzle, this is the, I hope all of you have seen this puzzle. The tiles are scrambled and you have to bring them back to this. There is one empty slot, and your only move possible is to move the adjacent tile from any one of the 4 adjacent positions into that position. You can slide a tile left, right, up or down if you have a vacancy in that spot. So 15 can go here, or 12 can go here, and then there'll be vacancy here, and then 11 can go there, and so on. So in formulating this, you can formulate as a state space search problem, right? But then one interesting thing that you can do is you can define a value at each node such that Gn is the cost of getting to this node from the starting state, which is easy enough. You actually got there, so you know how many hops it took. And Hn is a heuristic function, which is an estimated cost of getting to the goal state from n. And this heuristic function h is called admissible. That's just a name, made-up name, if it is an underestimate of the true cost. Now, of course, 0 is an underestimate of true cost, but it's not very good, but it will do. So you can use a heuristic function that's 0. But for the 15 puzzle problem, do you know, if you're given a scrambled set of tiles, can you say, oh, solving this is going to need at least these many moves? How many? You can say, how many tiles are out of place? 5 of them are out of place. At least those 5 have to move once to get to their real place. So that's one lower bound. That's admissible. But you can do slightly better than that, a higher bound, which is for each tile, how many spaces does it need to move to get to its correct place? And along Manhattan distance, right? Manhattan distance being along the x and the y axis. So when you move one tile, you don't move any other tile. So every tile's movement have to be at least that many, right? And so if you add them up, that gives you your h function, the heuristic function. So if you have a heuristic function like that, then what is the thing to do? Then the thing to do is to organize your open nodes, the so-called number of states that you have not sequentially, the number of states you have not looked at, into a queue ordered by their f value, right? F value includes the g, which is how long it took to get there, and h, an estimate of a lower bound of how many more moves are needed. And so the most promising solutions you try first, so the smallest f values you try first, and then that guarantees that if you find a solution, it will be the best solution. You don't have to keep looking for maybe there is a better solution further down in the tree, in the remaining open nodes. You don't have to do that. So that's the guarantee that a star algorithm provides. The A star algorithm basically says, as long as you have an admissible function, organize the set of nodes you haven't, states that you haven't yet explored in the order of their f function values, and then pick them only the smallest f value first, and you are guaranteed that you will find, the first solution you find will be the best solution. If you try to do this in parallel, well, first of all, by the way, those of you who learned this in AI, I don't know if they still teach it that way. They say every time you generate the children, put them back into the queue and sort it. Is that how you learn it? You pick one node, the best f value. It has 4 children. You have to put them, the queue has to be organized so that you can pick the smallest one from there first, right? So Lisp solution or something like that. You just say, put them in the queue and sort it. But logically that's true, but sorting will be a horrendous thing to do there. You just want to insert them back in a, what data structure? You want the smallest value every time that you will delete from the queue. Heap, delete min, a heap. You insert and you delete min, so a priority queue or a heap is the data structure to use there, right? But this is all great sequentially. How do you do this in parallel? And another problem with this for getting parallel is how much memory do you need? Oh, it turns out the memory can be as large as breadth first search, because you're generating something, you're putting in the queue in the right place. Its child may not be the best one. You have to go someplace else. I mean, so in the tree structure wise, you're jumping back and forth into different places, and your memory usage might be exponential in the depth of the tree. So one idea that Richard Korf came up with in the 80s is the idea of, so those were the 2 questions, how to control memory and how to do this in parallel. So depth first search, when you go to child and go to his child and go to his child, is space efficient. The amount of memory you need is proportional to the depth of the tree, right? But priority queue is not. It will give you a breadth first like behavior. So the idea in sequential was to do repeated depth-bounded depth first searches. So you say, hey, to this 15 puzzle, is there a solution in 2 moves? Then if not, is there a solution in 3 moves? If not, is there a solution in 4 moves? Well, it turns out you don't have to go 2, 3, 4, 5. You can jump in steps of 2. Reason for that is interesting. It's just a parity argument. But at the very beginning, you can see what the Manhattan distance is, and if that's even, then you're going to need an even number of moves. And then, so you either have 12 moves, and if 12 doesn't work, then you have 14 moves, then if not, you have 16 moves, and so on. So you can just do it like that. Well, for each depth-bounded search, you're just doing a depth-first search. So it's, again, this is sequential. So you're just kind of doing depth first, go down, come up, go down, come up. That means you just have a stack whose size is equal to the depth of the tree, and that's all your memory need is. And still, you have the property that the first solution you come across is the best solution. But aren't you duplicating the search? Yes, you are. When you're doing the entire search tree up to depth 10, is there a solution of depth 10? You explore those nodes, and then you say, okay, didn't find it. Is there a solution of depth 12? And you again explore the nodes that you visited before. But luckily, the number of those nodes is small. You can see that, right? In the binary tree, the number of nodes at every level, the number of nodes doubles, right? And even though you draw a tree like a triangle, it's actually more like an exponentially growing frontier there. And so, yeah, you duplicate some part, but the cost of duplication is maybe only 2-fold. And that's not, and you make up for that hugely in your memory cost and the feasibility. And if you live within small memory footprint, your performance will be better as well. The thing is, you can actually do this in parallel. But to do this in parallel, what you do is you do a depth 10 search, and then that search comes and winds down. Then you do a depth 12 search, and that winds down, didn't find it. And this searches you can do just by our first algorithm, just a regular search for a solution algorithm. And so those searches tend to look like this. Maybe if you are lucky, go to full utilization, stay there for a while, and then come down. But they have these peaks and valleys. Y-axis here is the utilization of processors, and so amount of parallelism. And so if anything that's not utilized is idle processor. So you're going to see lots of idle time. So this was one of my group's earlier work. We just said, well, we can actually overlap. You can just assign priorities to these iterations so that if you don't have work from this iteration, you will do work from this iteration. And so then these values get smoothened out. So that was the nice way of parallelizing the IDA star algorithm. I'm going to stop with that. I'm going to mention the fact that there exist all these other interesting problems, but we're not going to get into them.
All right, I guess we're ready to get started at this point. Obviously, I'm not Sanjay, but I'm one of his grad students. My name is Eric. So today I'll be talking about parallel discrete event simulation. It's obviously a type of simulation, and it's something that we want to run in parallel to get good performance out of it. So just a very, very broad, basic classification of different kind of computer simulations you might run into. You have either a simulation is either continuous or discrete. Obviously, since discrete is in the name, we'll be focusing on discrete simulations. And then furthermore, when you're looking at types of discrete simulations, you often either have them time-stepped, where you have some particular time step in mind for the simulation, and you update all your variables at that particular time step, and then move forward by some certain increment, and then update at the next time step, etc. But obviously, again, since event is in the name of what I already mentioned, we're going to be talking about event-driven simulations, where instead of being controlled by taking regular steps in time, you now have some set of events that you care about simulating, and all of these events occur at various points in time, and so you execute these events in order to finish the simulation. So you no longer necessarily have a regular step in time that you take, but instead that's the amount you move through time is dictated by when the events occur in time. So basically, discrete event simulations are broken up into what's called logical processes. So you take your simulation, whatever you're trying to simulate, you break it up. You break up the state into multiple LPs. Each of these LPs execute whatever events are targeted for that particular LP. All of executing an event on an LP updates the state of that LP. And so by the end, you've started in one particular state, you move to some other state, and that's the final result of your simulation. All of these events have a virtual timestamp, and so these events must be executed in order to get the correct result at the end of your simulation. There's a number of applications. I've listed a small subset here. It's common for analyzing traffic, for example, where events might be cars arriving at an intersection, leaving an intersection, crashing, etc. Military battles, networks, and by this I mean both wireless networks or supercomputer networks, where events might be packets moving from one router to another. Circuit simulation, getting down right to like AND and OR gates and how the signals move through these circuits. Economic models, and then just a number of other simulation types and applications here. So PDES covers a broad area of interest. So first, I'll just talk briefly about what the sequential implementation would look like, because overall, it's not a very complicated problem to do sequentially. Basically, if you have a single event queue that's some sort of sorted data structure, usually something like a heap, you can put all of your events into this single queue and then simply go through the events one at a time in order, executing each one as you pull it out of the queue. And basically there, all you care about is, as long as your queue is reasonably efficient at keeping things sorted, you're going to get an efficient simulation. And it's overall very simple algorithm. Just to show pictorially what it looks like, let's say in this case we have 3 LPs, A, B, and C. We have our event list here with each event having a timestamp and the LP that it's targeted at. And then on the right, we just have a notion of what our simulation time is. So we start at time 6 in this case. We take the top event off of the event list and execute it on the LP it's targeted for, which in this case is A. In executing this event, A might generate a new event for the future. Let's say this one happens at virtual timestamp 15 and is targeted at C, so that gets put into our list of events. And pretty much that's just how we go through. We just keep pulling out the top event, executing it. Executing it may create new events for the future, so we put those back in the queue. And eventually we hit the end and we've run our simulation. So the pseudocode for this also looks shockingly simple. You just have an event list. You pop the top event off, execute it on its destination, and just do that over and over again until you run out of events. So if it's so simple, what are the limitations, and why are we looking to do it in parallel instead? Well, a lot of these simulations, we want to go to a very fine grain of detail to get the kind of fidelity that we're looking for. So you're going to end up with something like millions of LPs. For example, going back to the example of traffic simulation, if you want to simulate the traffic, for example, in New York City, you're going to have millions of cars, a large number of intersections, different kinds of cars, bikes, pedestrians, etc., that you might want to simulate. So you have millions of LPs. And again, then in terms of events, you also are looking at generally billions of events to simulate. So if you try to do all this sequentially on a single core, these simulations are going to take forever. So we want to look at parallelizing this. What are the challenges we're looking at to parallelization here? So one thing that's important is the events that you're executing. Generally, they're very, very fine grain. It's usually something like updating a queue or just updating this a couple of variables in a state. So it's not like other parallel applications where maybe you have a giant matrix multiply and that's the operation you're doing. So you can actually take that single operation and split it across processes. In this case, events, we can't really take the work of a single event and spread it across some number of cores and get efficiency that way. But like I said before, these simulations do have billions of events. So instead, our parallelism is going to have to come from executing many events at once. However, like I mentioned at the beginning, we still have to maintain order in the timestamp. So now the challenge becomes, how do we execute as many events as we can while still getting the correct answer at the end of the simulation? So to parallelize this, we want to take our set of LPs and distribute it across all the processors we're running on. each processor now will have its own event list and virtual clock. So at least within one processor, we can still more or less follow that same sequential algorithm of pop the top event, execute it on its destination, and update our event queue, and then move on to the next iteration. However, across PEs, how do we synchronize our event lists and clocks so that we still know that we're executing events in order and we're getting the correct simulation? So the first very, very naive implementation that no one would ever actually do, but just to give an idea of the sort of approach we want to take, is now if we take our pseudocode from before, we just have a while loop. And again, the main idea here in the while loop is to pop the top event, get the LP that it's aimed at, and then execute that event. Now we just want to make sure that this event is actually the global minimum event. So here, instead I've inserted an all reduce, where we reduce the sim time, or the simulation time, to find the minimum across all processes. And then once we do that, now we check to see if our event is the minimum event in the system. So this gets us running in parallel. It has our LPs distributed across processes. But obviously, there's some problems. The benefit, it exactly matches the sequential semantics. So we know we're going to get the exact same event execution each time. The problem is we have no parallelism. We're still executing one event at a time, basically, unless some events occur at the same timestamp. But for the most part, we're executing a single event, and we have way too much synchronization. Every iteration, we're calling an all reduce and executing a single event. So to run this in parallel, we need to figure out some way how we can relax the ordering restrictions while still getting the correct result at the end. Because with this very strict ordering restrictions, we won't be able to get any parallelism whatsoever. So basically, we need to figure out what the fundamental problem is we're trying to avoid. If we want to relax this, the restrictions so that we don't have to follow event order exactly, well, we still need to figure out when will there be a problem that will cause an incorrect simulation. So let's say here we have two different processors, PE0 and PE1. We have 6 total LPs, A through F, and each processor, again, has its own event list and is maintaining its own local simulation time. So what we want to know here is, can PE0 safely execute events? If we look at our total list of events, we see that PE1 has the minimum event at timestamp 4. So we know that 4 can be executed correctly. The issue is, if we look at PE0, can that do any work as well? So we see it has an event at timestamp 6. Basically, are we allowed to do that? So the problem would arise is, what if the first event we're executing on PE1, this 4D here, when we're doing that, what if D then generates a new event targeted for LPA at timestamp 5? Now we've got a problem, because if A had already executed the first event in the queue, which is at timestamp 6, essentially A has moved past virtual time 5, and now we're asking it to do something at virtual time 5. We're asking it to essentially go back in time, and that is going to be what we call a causality error. That is where we'll get incorrect simulation results. So again, how do we ever actually guarantee we can execute events? How do we do this in parallel without running into problems? So there are two basic approaches in parallel discrete event simulation that you can take to synchronize. The first is the conservative approach, which basically says don't ever screw up. We only execute events that we know are safe to execute, and we have to synchronize off and determine which events are safe to execute. But once we do that, we know that each processor can execute these safe events without having to worry about causality violations. The second approach is the optimistic approach, where we say, let's just execute whatever events we have as freely as we want, and if we screw up, we'll fix it later. So basically, that is realized by rolling back a process if there is an error, which I'll go over a bit later. So the pros and cons in a very simplified sense of these two approaches are, in conservative, you have more synchronization, less parallelism, and less flexibility. I'll talk about what the flexibility means in a little bit. Those are your basic cons. But it is simple to implement, which we'll go over next. Whereas optimistic, there's a lot less synchronization required in most cases. A lot more potential for parallelism, because every PE can now execute events as freely as it wants. It's more flexible in terms of how the model has to behave, which I'll go over again later. But it's complex to deal with, because now you have to basically figure out how we're going to do these rollbacks. So for the conservative approach, there's a number of different ways in which you can determine whether events are free or are safe to execute. Probably the most common, does anyone have questions, by the way? Is that a question? Okay. So probably the most common is the windowed approach. This requires a model-specific look-ahead. So this is what I was talking about, where this approach is less flexible. It requires extra input from the model. So if you're running a traffic model, what we refer to as look-ahead will be different than if you're running, for example, a military simulation or an economic simulation. But basically, in this case, we have a look-ahead of 3. So the look-ahead is what a guarantee that the model gives on the minimum difference between the event you're executing and any new events you're generating. So a look-ahead of 3 just means if I'm executing an event at time x, the earliest I can generate a new event is time x plus 3. And so now we can determine what events are safe by looking at the window that starts at the global minimum and extends until the global minimum plus look-ahead. So in this case, which is the same example we had before, we see our minimum events is 4 over here on the right, which means our global minimum is 4. And if our look-ahead is 3, we now can execute, in addition to 4, we know 5 is also safe to execute, and the event at time 6 is safe to execute because they all fall within the look-ahead window. So we've gotten a little bit of parallelism back, but again, it depends on the model. If your model is able to have a high look-ahead, then you can get a lot of parallelism. If, however, by the nature of how your model works, the look-ahead window is very small, then we still run into the problem of you don't have much work to do at each individual synchronization step. And as I said before, this is only one type of conservative synchronization. There's a number of other different synchronization schemes that involve different protocols for determining who you send events to and knowing what your minimum event you might receive in the future is. But the principle always remains the same in that you have to somehow determine when is the next event I could possibly receive, and then only execute events that occur before that time. So we do notice it's very similar to the naive solution, where we have to do an all reduce to figure out this global minimum. And then instead of just executing the minimum, we now have a window, but it still, again, depends on the window that we're looking at. Also, the workload can end up unbalanced in this case. So if we go back and look, in this particular instance, PE1 has 2 events it can execute safely within the window, whereas PE0 only has 1. So next, we'll talk about the optimistic approach. So in the optimistic approach, again, we can execute events freely, and then we just have to figure out how to sort of account for errors when we make mistakes. And this is going to come by be in the form of what we call a rollback. So basically, if you receive an event that is smaller than your current event time, you know you've screwed up. And basically, you have to figure out how to get your processor to go back in time to a point before that event would have arrived, and then you can continue forward execution. So some questions that come up here is, how do we actually do this rollback efficiently? How do rollbacks affect performance? And how many PEs will a single rollback potentially affect? So again, there are a number of different ways in which you can actually do this type of synchronization. The first sort of proposed way of handling this is actually something called state saving, where at each virtual time, or at each, maybe not necessarily each virtual time, but every so often, you save the state of your LP, and then if you have to roll back, you go back to that previously saved state. However, a somewhat newer approach that is what I'll be talking about here is actually reverse execution of events. So this is what a small 2LP example might look like in an optimistic simulation, with a couple of important stats over there on the right. So let's say we start executing. Not necessarily, it won't necessarily always be the case that every LP is going to be executing sort of in lockstep with everyone else, but for simplicity, that's what we see here. So if each LP executes an event, we see that as we move forward in time, the total number of events we've executed is increasing, and the LPs are progressing through virtual time at a different rate. So in this case, LP0 has already gotten to virtual time 13, whereas LP1 is still back there in virtual time 4. And now let's say, while executing the event at time 4, LP1 created a new event at time 5 for LP0. Now, at this point, LP0 has already moved forward all the way up to time 15, so now we have to roll back. So to do that, LP0 will reverse the effects of the event at 13. Then it will reverse the effects of the event at 6. And now we're at a point in time where we can go ahead and insert 5 back into our event list, and now we can go forward back in the correct order. So now we've executed a total of 6 events, and I've only had 2 rollbacks. Another thing to mention is that LP1 could have continued forward execution, but again, just to keep this small example simple, it kind of stopped where it was, so I could show the rollbacks. Now we can continue forward execution safely. And now we notice, again, we are going to have some difference in the virtual times where LP1 has already now moved all the way forward to current time 15, where LP0 has now gone back to time 6. So this, so far, has, it works. One potential issue we see, though, is that after executing an event, we now need to save all of the events we've ever executed in order to be able to go back in time. And if we're going to be doing a simulation where we're executing billions of events, that the amount of memory to save billions of events is going to stack up, and we're going to run into a problem. And similar things happen with state saving. If you need to save your state at certain intervals of time, if you are executing for a long amount of time, you're just going to get more and more and more and more memory requirements until you eventually run out of memory. So how do we deal with this? Well, we handle this by doing what's called the GVT computation, or the Global Virtual Time computation. So this is a computation where we briefly pause the simulation and we figure out what the minimum time of the entire system is. So in this case, the current time is 6, or the minimum time is 6 because we only have 2 LPs. But in general, we have to examine every single LP in the system and all the events that are also in flight. So we need to do a complete barrier, wait for all the events to be received so we have an accurate representation of what the current time is. And then once we know that we have this minimum time and we can let all the processors know what the minimum time is, we now know that it's impossible for any rollbacks to happen that would require us to go before time 6. Because everyone has at least made it to time 6. We're not going to create any new events for time prior to 6. So now we can do what's called fossil collection, where we commit and free any events that occur before time 6. So committing, not only do we free the memory, but this also allows us to commit effects that have side effects. So for example, if you need to print a file or print to the screen, obviously you can't do that the first time you execute an event because you might have to roll it back, and it might be the case that that event was never supposed to be executed in the first place. So at this point, we would do things like printing out to file or any other side effects that can't be rolled back. And so here we notice now we have a total of 8 events that have been executed. 2 events have been rolled back, and we've committed 5. And then to make up for the extra event, that's this event 10 right here, that we've neither rolled back or committed because we don't know yet if we're going to ever need to roll back that event or if we'll need to commit it at a later time. So this brings up the notion of event efficiency, where we just look at the number of committed events over the total events. So in this case, it's 5/8. So this particular small simulation is running at about 62% event efficiency. Ideally, we'd want to be running at 100% efficiency, which just means that every single event that we execute is meaningful and useful to the final result, which means every single one has been committed. So another important thing to note here, so far this very small example sort of glossed over some of the details of what a rollback entails. So it might seem a little nicer than it actually is. So if we go back to the point where we have to roll back. So what does it actually mean at this point in the code when we have to move forward and reverse the effects of 13? So in the simple case, we just have to change the state of LP0 to go back to whatever state it was at before event 13 was executed. However, what if in executing event 13, we created new events for the future? Now, those events also should have never been created, so we need to reclaim those events, which those events may have already left our processor. They may have already been sent elsewhere, and they may have already been executed. For example, what if event 13 is what actually created this event 15 down here, and while we're in the process of rolling back, LP1 has already moved past event 15. So the issue here is that these rollbacks, if your simulation isn't behaving nicely, these rollbacks can kind of stack up, and you end up with this cascading behavior where rolling back a single event actually causes you to have to send out what are called anti-events to chase down all the events that were spawned from that event. It can cause rollbacks on other LPs and other processors. So even though we've exposed a lot of parallelism now, we just have to be aware that this parallelism can come at a cost when we don't have a high event efficiency or when we have poor rollback behavior. So overall, to summarize basically what I've talked about so far, like I said, when you're looking at a parallel discrete event simulation, you have two main classes of how you do the synchronization when you move to a parallel regime. So conservative is low parallelism and high synchronization cost. And it's very model dependent. If your models allow for high look ahead or allow for certain of these other synchronization schemes to work well, then maybe things will go fine. However, if your model has no look ahead or very low look ahead, and you can't figure out another synchronization scheme that will work well for your model, then you may end up with horrible performance. But it does have a low memory footprint, since you know every time you execute an event that the event is actually part of the final result, and you can free its memory. You also don't have to worry about how to reverse an event, which is an extra concern with optimistic. But optimistic, again, has generally high parallelism and low synchronization cost, assuming you have a well-behaved simulation. It's fairly model independent, and in that sense, I mean, you don't need to know specific look-aheads for the model or the communication patterns of the model for this to work. It can be memory hungry in that you need to keep around potentially millions of events at a time before you know which events can be committed, and your rollbacks can snowball. One other thing I haven't mentioned here is that you do also generally need to, if you're doing reverse execution, you need to also provide the definition of reverse events and how you actually go about reversing events, which in some cases is very simple. It's just changing state. And in other cases, it can be quite complicated to make sure that every single thing you do with an event moving forward actually gets reversed correctly when you execute it in reverse. And this is actually something that currently going on in the field that is we're looking into how compilers can actually generate reverse code for you. And it's a problem not necessarily specific to PDES, but it's an interesting problem nonetheless. So to kind of wrap up or go beyond the very basic description of what PDES is, I'll now talk a little bit about what Sanjay's group, and mostly me, is doing in the area right now and sort of how we're trying to push the field forward a little bit. So here is a current example of what PDES performance might look or looks like at very large scales. So where my work in the field kind of started was we were given a simulator that was written entirely in MPI, and we wanted to show that when you move from an MPI-like paradigm where you have usually bulk synchronous communication and everything's all your sends and receives are fairly synchronized, if you move instead to a model like Charm++ where you have asynchronous messaging, parallel objects, and stuff like that, how that would benefit PDES, because it much more closely matches the sort of the idea of PDES, where you have objects sending each other messages in parallel. So this is a comparison of the two different versions. The hollow points here on the bottom are the MPI version, and the solid points are the Charm version. And these are for 3 different job sizes, ranging from 500,000 cores up to 2 million cores for the blue lines. So running at very, very large scales. The y-axis is event rate, so higher event rate is better. It just means more events per second that you're actually successfully committing. So we see that in general, especially as we increase the remote communication, which is what the x-axis is, the Charm version is able to run much more efficiently because when you have such a high amount of very fine-grained messages, which are what the events end up being, you need to make sure that you're doing a very good job of overlapping the work for actually executing those events with the actual sending of events. Whereas if you were to send an event and wait for its reception on the other side before continuing, you'd end up with a lot of synchronization overhead and a lot of communication overhead, which is somewhat shown by the worst performance in the MPI version. And the other nice thing to note, it's not quite as clear from this plot, but we do see as we increase the job size from the red to double the amount of nodes of the green to double the amount of nodes in the blue, we are getting fairly good scaling and efficiency in terms of we're also roughly doubling the event rate we're seeing. So these results are all nice and good. We see very high event rates in general. In the billions of events is what we would like to shoot for at these kinds of scales. So we're seeing high event rates and high parallel efficiency. But this is for a particular benchmark in PDES called phold. And this benchmark, you have a very uniform workload. Basically, when you receive an event, you generate a new event for some offset in virtual time, and it's directed at an LP chosen completely at random. So you have this very uniform distribution of events and timestamps throughout the entire simulation. So everything is balanced and works out pretty nicely, which means, in general, our rollback performance is going to be good because every single LP and PE in the system is moving forward at roughly the same rate. So where my work has sort of taken me more now is what happens when we have imbalanced models. And this kind of goes back to the worries I mentioned of the optimistic execution and how the rollbacks can sort of spiral out of control. So this is a plot showing phold. It's now, instead of showing event rates, it's showing actually the number of events we're executing. So the green bars here are the number of events that we're actually committing. And that, remember, an event that's committed, that's the only event that we actually care about in terms of the final result. Everything else is just noise and side effects of the optimistic execution. So you notice for each of these three different configurations, which I'll talk about in a second, we have the same number of committed events. So we have the same exact result that we're looking for. But now we've introduced a couple of different types of imbalance. So work imbalance is where certain LPs take longer to execute certain events than other LPs. Event imbalance is where there's a slight perturbance in the distribution. So some LPs have more events than other LPs. And then the combo imbalance is just a combination of these two. So some LPs take longer to execute events, and some LPs have more events. And so once we get away from the very nice uniform balance of the baseline configuration for phold, we start to see the effects of the optimistic rollback problem creeping in. So here the blue lines are the total number of events we executed during the simulation, and the red are the rollbacks. So in general, well, it's the case that the blue plus the number of rollbacks plus the number of events committed is going to equal the total number of events. So that's where those numbers come from. And we see for the different kinds of imbalance, even though we're only committing, in this case, around 17 billion events, in some cases it's taking 19 billion events, or in the combo case, actually up to 23 billion events to actually get to the final result of our simulation, because we're ending up with less efficiency in our event execution and therefore more rollbacks. So essentially all of this extra time executing events in the forward direction and all of the time down here taken to actually roll back these events is extra work that we wouldn't be doing in the conservative case. In the conservative case, we would just be exactly executing the green number of events. So despite the fact that we have this extra parallelism that's exposed through the optimistic synchronization, sometimes it's going to result in a lot more work. And so how do we address that, and how do we fix that problem so that we get more efficient execution? So what I've been looking into lately is load balancing. So basically, in PDES, we want to figure out how to do load balancing so that not only we get good balance in how much work each processor has to do, but also how does that affect event efficiency, and how do we make sure that this work we're balancing is actually useful work. So here is some of our earlier results where we just look at, again, these same configurations and their event rates. Oh, and one thing I want to mention about the previous slide is the exact effect that this lack of efficiency has on event rate. So at the bottom here, I've listed the approximate event rates of each of these configurations. And we see that even though they're executing basically the same number of committed events, here we're at 83 million events per second, whereas all the way over in combo, we're only executing at 53 million events per second. And in the case where we don't have any imbalance and we're still executing the 17 billion events, we're looking at around 105 million events per second. So this loss in event efficiency and all this extra work we're doing has a pretty significant effect on the time to solution here. So here we're plotting the event rate. So again, higher being better. And we see we have in blue the no load balancing case, which is the same as we saw in the last plot. So around 73 million events per second. 83 million events per second, 78 million events per second, and 53 million events per second. But now when we introduce load balancing, so we've used 3 different strategies for how to balance the load here, which is essentially just taking those LPs and migrating them to redistributing them across the processors so we have a more even distribution of work. We get higher event rates. So now, especially if we look at green, which is a greedy load balancing strategy, we bring it up to around 93 billion events per second in almost every case. So we're able to somewhat deal with this event efficiency issue by just redistributing the load. But the other question that we're looking at answering is what exactly is load in PDES? So for most other parallel applications, the load of an object is just how much time it takes to execute, especially when you don't have things like speculative execution like we do in PDES. You know every object is going to do the same exact work in a given run of your parallel application. So if you measure how long it takes to do that work, that's roughly equivalent to what the load of that object is. So if we redistribute based on that, then we'll get roughly the same amount of work on every processor. However, now when we introduce rollbacks and this notion of committed events versus rolled back events, how do we actually balance the load? You can imagine a scenario where you have one LP that's executed 10 events and committed all 10. So all 10 of its events are actually useful, meaningful to this final result and work we had to do. Whereas another LP that also executed 10 events but rolled back all 10 of those events, essentially it hasn't done any meaningful work yet. Whereas the CPU time taken by both objects will probably be roughly the same, maybe even higher for the one that was doing the rollbacks. That doesn't correlate to the amount of useful work each object has done. So sort of as second last slide. Ignore what I just said. So this slide just goes off of the previous results to show exactly where these increases in event rates are coming from. So here we have the 3 different configurations, and we have 3 different colors for the types of events. So the red are the number of events rolled back every so often throughout the simulation. Green is the number of events committed, and blue is the total. And so what we've plotted here is the GVT number down at the bottom. And then after we've computed the 64th GVT, we do load balancing. And we see that after the load balancing now, for most of the configurations, we're not only rolling back less events, but we're also committing more events. So the performance improvements here that are getting us faster time to solution are primarily coming from the fact that we're now executing events more efficiently. So now getting back to what I was saying before with how do you measure load in PDES, since we want to essentially take into account only useful work for when we do load balancing, the CPU time spent by each object might not be the best way to go about doing that. So from this plot and from the previous plot, we see that if we do balance just based on how long we spend executing each LP, that gets us somewhere. But we want to know, what we ultimately want to know is, can we do better? So for this plot, again, we have event rate on the y-axis, so higher is better and just faster execution. And what we're comparing here is a number of different metrics for determining what the load of an LP actually is. So the blue bar on the left is no load balancing. So this is where if we have load imbalance, we're going to have poor performance due to bad efficiency and also bad balance of load across the processors. Green is the CPU time, if we use CPU time as the metric. So that's sort of what I just showed in the previous plot. So that gets us improvement. Sure. But then we're also looking at a number of other ways to measure load and then do load balancing based on that. And so what we notice is the highest performing one here is actually this purple, and that is the number of committed events each LP has executed. So this is a way to take into account only the useful work. So if we go back to the case where LP1 has executed and committed 10 events, or LP2 has only executed 10 events but rolled back all 10, now the first LP would look a lot heavier because it's actually doing meaningful work. Another metric that has also performed well is the pending events. So back in the examples, we always had some idea of what work we were going to be doing in the future because we have this list of events with timestamps that we will be executing in the future. So we can also use that to, instead of predicting our performance based on what we've done in the past, actually just look at what work do we have to do in the future and use that to try and figure out what our load is going to look like in the future. So far, this is sort of the current state of the work. We just have a slew of these different ways to measure load, and we're trying to figure out which is going to be the best. And that's kind of where my research leaves me now.
So, 2 points. First of all, this was not a research presentation. This is a, but since that's research, we have made part of it that. But it's a PDES area, representing the PDES area. I think we all got an idea about what parallel discrete and simulation. In fact, if you talk to other people in HPC about PDES, well, you can tell them what the other meaning of PDES is. It's not pronounced that way. Parallel partial differential equation. That's the other dominant, right? The question for you is, you said earlier that committed, just measuring the load of objects is not enough, because here is an object that is moved forward 10 times and came back and moved forward again. It shouldn't count all that work as its work. On the other hand, it's maybe one of those objects that is prone to rollbacks, right? That is to say, it gets messages out of order more often because of the nature of that object. And so some of that rollback should come from it.
Yeah, so that's why, even though when I initially presented the optimistic synchronization, everything seems all nice. We have all this parallelism and so much less synchronization. But then this is where all these other issues start creeping in, and it's less clear what an object is going to do and what amount of that is actually meaningful, and then how to measure these objects. So that's why it's sort of an interesting area of research. That's the next step. Either using some sort of combination, just like adding the number of committed events to pending events, or also doing something where the load balancing strategy itself can look at all these different quantities and say, okay, for this particular, based on what I've been seeing, maybe now we want to balance based like 70% on committed events, but like 10% on pending events or something like that. Yeah, something with machine learning might also be able to determine, based on the model, that how it's been running so far, not only how often should we load balance, but which of these metrics is most important to predicting future performance of this model and getting the best, not only efficiency, but also load balance. Sorry, can you repeat the first part of the question? So that's another thing that sort of depends. Usually, it's just what you've done since the last load balancing iteration. And so I mean, for most of these, it's just like a counter. So it's not like not very memory intensive. So even after we've committed events, we get rid of the memory for the committed events. We just know that we've committed like 10 events since the last load balancing period.
The basic answer is the sample per runtime typically does trace and keep track of this string, but in a collapsed form. And you want, I think you are hinting at this, you want more recent history rather than all history. And so you can turn off tracing and turn on tracing a little bit before you want to do that. Sorry. Yeah, no, like I said, it's collapsing. So it's just keeping track of the total load for the object during this period. And the tracking load itself is not heavy because it's timer cost. The timer cost is really getting. So neither from memory point of view nor from computation point of view, it doesn't get too expensive.
Well, there is one case. I mean, it depends. Again, it depends on what metric you're using. But one of the other default metrics in Charm++, not only will it measure CPU time, but it'll measure some notion of communication and a communication graph. So actually, in cases like PDES where there's millions of objects, if we have tracing with the communication tracing turned on, then we do generally like run out of memory. It takes longer to analyze that tracing graph because it's so large and complex.
Unless the communication pattern.
Yeah, unless the communication pattern is sparse. But yeah, for most of these metrics that I'm measuring, it's like each one just is a single double that we keep track of and update throughout the execution. Yes? Yeah, so that's sort of like a more general load balancing concern of the like locality of is migrating the object worth it or not. So that's usually in cases where you have like larger amounts of load imbalance. That's getting the better balance greatly outweighs just the initial hit you take for relocating. But there are also certain load balancing strategies. So I didn't really go over. I went over the different metrics for measuring load, but here, like we've saw 3 different load balancing strategies, for example. There's a number of strategies, and some of those try and, for example, minimize the number of migrations you're doing, and some of them don't. So if it's a particular problem where like relocating an object is going to cause a lot of overhead in that case, you would want to use a strategy that migrates less objects. So the measurement, like Sanjay mentioned, the measurement of like the stats is not application specific necessarily. You can make it application specific, but as long as you tell the application how to migrate your objects, there's not much that's specific to the application. It's all handled within the runtime, and the runtime does also measure things like background load. So if there's a lot of stuff running on one of the PEs, for example, you would know to put less objects on that PE because it has other work to do other than just what your application is causing.
But is there application-specific choice of strategies? I think for general Cham++, you might want to explain the meta-balance idea, and then for previous,
Yeah. So I guess for like we have a large number of strategies. So yes, certain strategies will work better for certain applications, and up until fairly recently, it was kind of up to the application developer to figure out which strategy worked best and experiment with different ones. But one of the other areas of research in the group is something called meta-balancer, which again goes back to some of the machine learning stuff where it, looking at the statistics of your application as it's running and where it's running and background load and stuff like that, it will try and figure out when to do the load balancing, when would be the most effective time based on how the load is changing over time, and also which strategy would be most effective based on your application-specific characteristics. So if load in your application is like really affected by communication, for example, it would probably choose a communication-aware load balancer, whereas that's not super important. It might choose a different load balancing strategy.
Oh, that does look like. In that case, wait for a minute. I might need to get. I didn't do it. That should work. Thanks. So I've pretty much been lecturing since morning, doing tutorial in my workshop. Parts of the tutorial are discussing, so my voice gives out in the middle, you know why. And my mind gives out in the middle like it is doing, you know why too. So what I'm going to do is, actually I want to test a little bit of what you learned. So what is GVT? Someone tell me what's GVT? Yeah. The timestamp of the earliest event anywhere in the system that's not yet processed, right? That's the GVT, omniscient GVT. But then the real GVT is, you have to calculate the GVT. It should always be a lower bound than that, right? Because at any point you calculate, there's no, in parallel computing is like relativity, there is no notion of simultaneity. So on one processor I say, hey, GVT is 500. Somewhere else it has already processed that 500 event, and there is no event other than 650 left in the system, right? So you'll always have an underestimate of the real GVT when you calculate it, unless you have some kind of a stop everyone, synchronize, find GVT, and continue type of scenario. But yes, the GVT meaning is exactly what you said. And I don't know if you saw the example of intersections and cars traveling through the intersections. Did Eric give that example? So imagine you're talking about all kinds of physical simulations earlier, right? Temperature in a room and fluid dynamics and particles moving and so on. Well, if you think about simulating traffic in a city with cars, now you have a problem, which is that real stuff happens only at the intersections, right? The decision making, variability. Otherwise, a car leaves an intersection, there's not too much traffic, it's going to get to the next intersection in a certain amount of time. So you really don't want to update the position of every car in your system for every millisecond time step, right? That will be wasteful, or every second times, half a second or whatever. So instead, you want events. When something happens, you want to change it. When it reaches the intersection, you want to decide which one will leave the intersection first and so on. So in those situations, parallel discrete event simulation is about the only way, and it's a very tough problem, one of the few problems that is really resistant to efficient implementations in parallel computing because of the causality violations. If you try to do stuff in parallel, you'll get causality violations, you'll get out of order messages in time, or if you try to constrain them to process only the ones that are for sure not going to cause causality violation, then you don't have enough parallelism. So that's what makes this problem very interesting.